Hi, everyone. We're the Argonne Data Science Clinic team. Now, I want to start by introducing the members of our team. We have our external mentor, Matthew Deering, who's the technical lead for the AI for Operations initiative at Argonne. Our internal mentor, Bill Troke, who's a preceptor in data science at the University of Chicago. And our TA, Cassie Tang. My name's Alex. And on the rest of our team, we have Uday, Rain, and Qilin. To give you a higher level overview of what Argonne actually is, it's a national laboratory with a focus on science and engineering research, and it's working to answer the biggest questions facing humanity. It's a federally funded lab that needs to maintain privacy and confidentiality within its research. With the popularity of generative AI models like ChatGPT, Argonne has decided to implement its own internal tool for research called Argo. Argo is the proprietary chatbot for Argonne, and it's trained to answer domain-specific questions from contextually relevant information. Argo currently uses a retrieval augmented generation, or RAG system, to generate responses with enhanced response quality. And it does this by retrieving similar documents that Argonne has supplied us with. So imagine if a user wants to know if the rules about handling dangerous chemicals apply. Our RAG system would be able to reference the relevant supplied documents about good practices with chemicals to help generate a more accurate response. For our project, the problem statement that we decided on was that Argo's current RAG system needs to be extended to better meet user needs. This is especially the case for streamlining both common task types and also ensuring compliance standards are met. And so this is where the use of our agent Lite systems comes into play. We're using agent Lite systems as a way to streamline certain processes of Argo. And we're doing this by using predefined patterns of prompts to generate more consistent responses for certain question types. Specifically, we're focusing on one, a literature review generator, and two, an organizational tool for sectional requirement information.
Thank you, Alex, for a start. So for the literature review part, we work on extending the Argo front end to support domain-specific tasks, specifically literature review generation. So the idea is pretty straightforward. The user input a research question and uploads relevant documents, and the system will automatically generate a literature review based on those inputs. It supports multi-format documents such as PDFs, docs, or even images. It parses everything, finds the part that answers the question, and returns a structured summary. We are also using local LLMs like Llama 3 to make sure the document content stays confidential, which is pretty important for internal or even unpublished work. We also offer a variety of models to choose from, depending on the task and compute resources. So here is a quick example of how it works. It is fast, organized, and super helpful when you are dealing with a lot of papers and need a quick overview. So here is a short demo video showing the detailed whole process in action. So the user uploads a document, enters a research question, and then the system automatically splits the response into 4 sections: introduction, findings, gaps, and conclusion. So to save time, I've skipped the actual waiting period doing generation in this demo. But in practice, you can see each section fill in live with progress bars. And once it is done, the final output appears below. It is nicely structured and tied directly to the input question. The whole process runs on the Argo platform through a simple chat interface, so it is easy to use and integrates smoothly into other tasks. And next, Uday will walk through the requirements.
Thank you, Rain. We will now go over our work on requirement management for Argonne. So to give more background, requirement management at Argonne focuses on automating the process of updating and retrieving requirement information from regulatory documents. This ensures that all technical and contractual obligations are clearly defined, traceable, and met, which keeps new research aligned with both federal and operational standards. To support this, we've built pipelines that extract relevant internal and external information and then store them into a vector database. This allows for fast and reliable access to the information whenever it's needed. To better understand the role of requirement management, we've provided an example of its process. Let's suppose that Argonne received a Department of Energy contract to develop a lithium sulfur battery prototype to improve energy storage. Once awarded, the project must comply with regulations such as FAR 52.203-13, which establishes a written code of business ethics within 30 days and implements a compliance program. Thus, the requirement management process includes 3 key steps for this project. First, it identifies all relevant requirements for the project. Secondly, it automatically detects and updates the project standards based on real-time changes to those requirements. And then finally, it ensures compliance by tracing each requirement back to the project and verifying that documentation, such as ethics policies, are in place to prove adherence. So having introduced requirements management, we will now outline a requirement information extraction process. This slide outlines the internal pipeline that we use to organize Argonne's prime contract information into our vector database. The process begins with taking a PDF version of the Argonne prime contract and applying optical character recognition, or OCR, to convert scanned or image-based documents into readable text. Next, the content is systematically extracted and organized by section and then parsed into manageable text chunks, which we then package into payloads. Each section is then specifically tagged as internal to facilitate accurate and efficient retrieval. Finally, these organized and tagged payloads are stored into our vector database, enabling seamless and rapid future access for decision-making needs. One problem that we ran into during the requirement management process was that some documents reference other external documents that weren't in our data set. In response, we developed a pipeline to locate these documents from publicly available sources and included them to improve our requirements generation process. Similar to our internal process, we start with OCR to convert the PDF document into machine-readable text. However, for external requirements, we specifically extract hyperlinks and references pointing to external clauses or documents. Next, these external sources are assessed, and the relevant content is scraped and then systematically summarized by section. These summaries are then parsed into text chunks and built into payloads that we then tag as external. Finally, these tagged summaries are stored into our vector database, again allowing for efficient retrieval and ensuring compliance with external regulatory requirements.
Thanks, Uday, and I'll continue to explain how our system automates the requirement extraction using both internal contract clauses and external legal references. So the process starts with an automated requirement query. Say that a user asks for the requirements about clause I5, and that clause number would be used to search a vector database that stores both internal and external content. The system retrieves the top relevant text chunks. We see here the external chunk from the US Code's website and the internal chunk in prime contract I5 section were extracted. While these chunks can be long and unstructured, we pass them to a large language model like Llama 3 with a prompt that asks it to identify clear obligations, especially phrases like shall or shall not, and the model then outputs a concise requirement summary that reflects both the contract's intent and any related legal obligations. The retrieval augmented generation RAG setup in the vector database not only augmented the search for external legal references, but also improved the requirement generation for clauses without any external links. The diagram here shows how RAG retrieves the most relative subparts like H2A, B, and C using H2 as a metadata for querying. Instead of passing the entire sectional content, the LLM receives focused, high-quality chunks. This avoids context overload and combined with few-shot learning leads to more accurate and structured outputs. Continue with the example from clause H2. The baseline model misses the key obligation and focuses on vague language. With RAG, the model retrieves subpart H2B, capturing the specific requirement of 5-year institutional plan updated annually, resulting in a clear and faithful summary. Numerically, when comparing LLM outputs to human annotations on the sentence level, we observe that cosine similarity improves from 0.15 to 0.82 in this case, and on average from 0.59 to 0.65 across all 202 clauses. This demonstrates that RAG not only enhances precision in individual outputs, but also yields consistent gains in aligning generated requirements with ground truth annotations. So to sum up this quarter, we delivered two key components. We have a literature review pipeline integrated into the Argo environment and the requirements management module that supports output generation and the similarity scoring against human annotations. Looking ahead, our primary next step is to fully integrate the requirements pipeline into Argo's architecture. This will enable end-to-end automation of requirement extraction, validation, and compliance tracking. Looking ahead, additionally, we plan to benchmark generated requirements and deliverables across a range of open source models, including DeepSeek, Gemini, and Mistral. Since different models may have exhibit distinct chains of reasoning, comparing their outputs could yield valuable insights into model alignment and interpretability. And that's the end of our report, and thank you all for listening.